So quiz Wednesday on Coulomb's law. Uh, it will be short. I'll give you some time at the end of class, but I'll try just making it due at 11:59. Make sure you complete it, uh, even if you get it wrong, just because it also is a check-in that you are participating in the class and do not need to be dropped.
Professor,
Yes.
can we do some of the homework problems since we already turned it in?
Yes, we can.
Thank you.
If there's something you want to go over, we absolutely can do. So homework, it was just due. Homework will be new next week. It will be posted tonight, and I'll get homework solutions posted. If not this afternoon, then by tonight. But if there is something that you would like to go over from this recent homework set, we can do that. So the quiz will be, I'll give you a block of time at the end of class, but it's not going to be due until the end of the day for Wednesday's quiz. No, it's going to be on Coulomb's law. So it will involve forces and one or more point charges. Well, two or more point charges. For what we're going to go over today, finish up chapter 21, look at dipoles, and start chapter 22. Our big topic is going to be introducing Gauss's law. So, any questions or things that you want to see before we keep going? Oh, I'm crackling. And you're letting me know, is this better?
Yep.
Beard noise.
It was immediate too.
Thanks for letting me know. Anything else? Hello. Someone wanted to do something with the homework? Are we good on it?
Could you review the last problem?
Last one? Okay. That one was much more conceptual than numerical. Big idea. There is something charged. Positive or negative isn't really going to make a difference. Let's just assume it's negative. So there are excess electrons on the surface, and someone touches it. So this person is a good enough conductor that electrons will spread out through them. They are all repelling each other. So if they can spread out, they do. Some of it ends up in the hair. And the bits of hair are going to push away from the nearby charges, say on the other bits of hair and the rest of the head. And spread apart from each other. So it's just like charges repelling. That's the big physics idea.
Okay, because yeah, I saw it on chapter 23 on the book,
Mhm.
and I quoted that because it has the same sign, positive sign or whatsoever. Would that be correct?
23? Haven't
On
gotten there yet.
Yeah, because I searched up on the search F the Van de Grasso generator.
Oh, yeah, it has a picture of it at the start of chapter
Yeah.
23. It does.
Okay.
The point was to explain what's going on in your own words.
Yeah, I said it each repels the
Yeah.
Hishran. So, and can we go with? Can we check number 3?
Sure. So there's a quest for 3 and a request for 4.
Wait, one more thing on number 6. Was that induction that happened to the hair, or is that just like having charges?
It's just having charges. So if the hair was being charged, if there was only induction going on with the hair, it would be attracted to charged things instead of repelling like it is.
Okay. Okay, thanks.
Also, for number 6, you shouldn't be grounded, correct?
Correct. If you are grounded, the charges will flow to the ground and you will get very little buildup inside of you.
All right, thank you.
Sure. For number 3.
Yes.
3 meters, 3 newtons, and we need our excess charge. And they're both negative. Cool. So we know that our force comes from KQQ over R squared. They have the same negative charge. So our force will just be KQ squared over R squared. And our distance is 3 meters, so 3 newtons. So this 9 times this 3 is going to give 27. So that ugly bit will give what the charge is. And this will give the charge in coulombs. From the coulombs squared, or inverse coulombs squared in K. So then you just need to convert it into electrons. If you know the force, you can figure out how much charge generated that force. Usually you have charges and you figure out a force from it. This one was just looking at it backwards. Number 4, number 4 is mathematically a little tricky. So there is a 2 coulomb charge and a 1 coulomb charge.
Excuse me, Professor, for number 3, do we have to divide that number by 1.6 times 10 to the negative 19?
Yes, yes, you do, in order to convert into electrons instead of coulombs.
Oh,
So we can have a setup like this. Number 4 is tricky. I agree. This is at 1 meter. So we're looking at a spot where the electric field would be 0. So just as a big picture to start off with, let's divide this up into 3 regions. We've got what's over here. We've got what's between them. And we've got what's over here. So at negative x, the electric field is going to be dominated by the charge which is both closer and bigger. So it's going to be going that way. The smaller charge also makes an electric field that goes that way. So they are working together to make an electric field going in the minus x direction. So the only way you're going to get to 0 at negative x is getting to infinitely far away when that 1 over r squared term kills it to 0. For positive x greater than 1 meter, both of those charges are creating electric fields going in the positive x direction, away from the positive charges. So they're going to add together. And the only way you can have them end up being 0 is if you go to infinitely far away, when the 1 over r squared term will kill it to 0. So what's left over is what's between the two. And the area between the two, they're creating electric fields which go in opposite directions. So it's at least possible that it would get these two finite things canceling out to 0. So if you are closer to the 2 coulomb charge, it's both bigger and closer, it's going to be stronger. If you're exactly halfway in between, the 2 coulomb charge is bigger, so the electric field it creates is going to be stronger. So the only way that they can cancel out is if they have equal magnitudes in opposite directions. So you need to find some spot that is closer to the smaller charge in order to give them equal magnitudes. So the condition we're looking for is the total electric field being 0. Yeah, x needs to be more than half a meter and less than 1 meter. So we can figure that out without really running the numbers. So the only way this works out, if the magnitude of E1 equal to the magnitude of E2, so we can call electric field 1 the electric field from the charge of the origin, electric field 2 the one at x equals 1 meter. So K, Q over our distance here, how far this mystery point is from the origin is just x. And for the charge, we can plug in 2 coulombs. And that needs to be equal to the magnitude of the electric field from the point at 1 meter. That's going to be K For the charge there, it's 1 coulomb. And we need to divide by this, which is a little bit trickier. But if x gets you from the origin to our point, 1 minus x will get us the rest of the way to 1. Because x plus 1 minus x equals 1 meter. So K cancels from each side of the equation. The coulomb cancels from each side of the equation. And then cross multiplying makes it look a little more manageable. And this is some algebra now. You could square root both sides of the equation. That'd make it look a little easier. We just need to be careful that we're not square rooting a negative, but both of these are positive, so we're fine. And I think that's our solution.
Wouldn't it be x plus root 2x?
Oh, yeah, it would. That's how algebra works. Good catch. K is 8.99 times 10 to the 9th if we're using our SI units. It's not K that's 1.6 times 10 to the 19. That's how we convert from coulombs into fundamental charge. So how many electrons you need to make -1 coulomb? Or how many coulombs 1 proton is, to be more accurate. If you use the quadratic equation and got there, good for you. Cool. Oh, the 1 minus x part, sure. So what matters is the distance from the point we're measuring to the charge. So this is just x, because we're on the x-axis, and how far from the origin you are is just defined as x. This is another quantity that we want, but we do know that they add together to make 1 meter. So x plus question mark equals 1 meter. So that unknown quantity is 1 meter minus x. Cool. Right. Let us move into dipoles. So a dipole is something that does not have a net charge, but it has its positive and negative charges separated. So that on the whole, in one direction, there's more positive charge, and in the opposite direction, there is more negative charge. So if we have something like HCl or water, in both cases, the hydrogen ends up with a less than its share of electron nearby, and that end ends up a little bit positive. And the chlorine or the oxygen, a little greater for that electron, that end ends up a little negative. So in addition to molecule scale dipoles, you could just have macroscopic dipoles. You could have just a meter stick, and at one end you hang your plus piece of tape, and on the other end of that meter stick you hang your negative piece of tape. Either way, there's some separation of charges. So all three of these objects are net neutral. So you would not call them a monopole. And so they are a dipole, two poles, positive end, negative end. And in a non-uniform electric field, you can get a net force on a dipole. But if we have a uniform electric field, we end up not getting that. So if we just have some positive charge, and some negative charge, and just allow our electric field to be perfectly uniform. So both of those charged ends will receive a force, but that force is just going to be the charge times the electric field. So if one of them gets pushed, the other one gets pulled, and there is no net force. But if you push something on one end and pull on the other, even without a net force, there is a net torque. So this dipole can be twisted by this electric field that it's in. So our torque is going to be the length of the lever arm times the force. If we look at the middle, we can have two forces acting on this. So our total torque. So our force on the top one is going to be the charge times the electric field. The length of our lever arm is just going to be the length of the dipole divided by 2. And because we have a cross product in here, we need the angle between our force and our lever arm, which is going to be the sine of theta. Or the sine of the angle. Give the sine theta. And there's also a torque from the bottom charge, which looks really similar. So the torque ends up being the charge times the electric field times the length times the sine of the angle between them.
Wouldn't the angle for the bottom one be 180 minus theta, or is it? Oh, we're measuring it from the other side. Okay.
So you can think of it as, yes, a different angle, but it's also a different charge, and it works out to give the same torque. So in this case, this one's going to get pushed that way. This one's getting pushed that way. So opposite forces, but they give the same torque. It can be convenient to be able to just some dipoles that don't have all of their charge at one spot. But you can still get a measure of the total amount of charge separation in this dipole. In the simple case, it's just going to be the product of the charge and the length. In the more complicated case, you need to integrate over that or add them up. So our dipole, we can characterize it as just one vector. P, its polarization, and for its magnitude, it's just going to be Q. So in that case, our torque is equal to the cross product of the dipole times the electric field it's in. So this is our P is our dipole moment. If this dipole actually does rotate, even though our item as a whole might not be having a net motion, the parts are. And if a force is acting on each one of them and they're moving in the direction of the force, work is being done on it. So our work is just the integral of the torque over the angle we do it on. So that total work
Professor, for theta,
yes.
why wouldn't you choose the theta on, say, the other side of the dipole? Like on the other side of the 180, why do you choose which
This one?
Yes.
So I'm going with the displacement of the positive charge as determining our dipole direction. So the P vector is going to point towards the positive charge. Just how dipole moment is defined. Good thing to get clarified. So integral is going to give us cosines from our sine. So the way it's pointing has some energy associated with it. It being in different angles, you need work to get it from one to the other. So having it go back the other way can do work on something. So if our potential is minus our work, so there is a potential energy associated with the orientation of a polar molecule in a constant electric field, a uniform constant electric field. If it's flipped one way, it would take energy to spin it around in the other direction, because you're going to be moving the positive charge against the electric field and the negative charge with the electric field, both of which take some energy to do.
So theta 1 and theta 2. So theta 1's kind of like what it is right now, the angle, and then theta 2 is like when you like spin it around a bit, what the new
Yes.
angle is.
Initial
Okay.
angle, final angle. Yes.
Okay.
We're going to work with this a little bit. Oops, this is wrong. What happened to my... There we go. Haha, life is good. So I'm not asking about the direction of torque. I just want the biggest value you could get it and the smallest value you could get it. If we have plus 0.05 coulombs and minus 0.05 coulombs. One centimeter apart from each other in an electric field of 100 newtons per coulomb. So see if you can work it out. So our torque. We are charge times our electric field magnitude times our separation distance times the sine of the angle between our polarization vector and our electric field. If you worked in centimeters and got a torque in Newton centimeters, less standard, but not incorrect. So our coulombs cancel out, and we're left with Newton meters, which is what our torque unit should be. So the maximal value that this can take is 0.05 Newton meters, and the smallest magnitude it could have would be 0. So if it is exactly aligned with the electric field or exactly anti-aligned with the electric field, there will be no torque on it. Good on
Okay.
this.
Sorry, can you say that one more time? So if it's aligned with, if it's aligned or if it's aligned horizontally with the field, it'll have 0 torque.
Well, horizontally and vertically,
Oh, sorry, it's relative. Yeah.
yeah, it depends which way the field is going, not which way gravity is going. But yeah, if we've got an electric field going this way, it's not going to be twisted. It's already in the optimal position, no torque. And if the electric field goes the other way, it's in an unstable equilibrium, but it still is in an equilibrium. There'd be no torque here.
Okay. So
If it
the minimum
twisted
torque.
1 degree, then
Mhm.
you'd be able to get it to keep going. But yeah, no net torque.
Okay, so our minimum torque is going to be if it's aligned with the field, which is 0, and then our maximum is 0.5 if it's perpendicular.
Newton meters. Yeah. So our minimum magnitude.
Newton meters. Okay.
Yeah.
So I'm picturing this like a weather vane in the wind. Is that like a valid way to think of it?
Yeah. Yeah. So if it's pointing the way it would normally point in the wind, where the less aerodynamic end is downwind, it will stay there usually. However, if it's perpendicular, it gets quickly whipped into position. But if it's exactly out of position, if the wind all of a sudden exactly changed directions 180 degrees, it wouldn't know whether it needs to turn left or right in order to fix it. So if things were a little bit off, it would whip around, but in that perfectly anti-aligned case, no torque. We're going to move on significantly. We're going to start building towards Gauss's law. Before we get there, I would like everyone to think about their favorite kind of power plant, a Dyson sphere. So our idea for a Dyson sphere is you take a star, and a few solar panels just not going to do it. So instead, you make a complete spherical wrapping around it entirely out of solar panels. So here's our star, and we coated in solar panels. Now we have a Dyson sphere. Some different super engineer found a star which is exactly the same size, same brightness, but they wanted to show us up. So they made a bigger Dyson sphere. So the question is, which of these Dyson spheres would get hit with more total sunlight? So you can think about where it's going to be brighter. You can think about surface area. Which one's going to catch, more rays total? So if they worked at the same efficiency, which one would make more power? The more popular answer is the big one, followed by it's a tie, and the small one is in last place. In this case, it works out to be a tie. So the big one has more surface area, but it is brighter on the surface of the small one. So just like it's hotter on Venus than it is on Pluto, if something is closer to the star, it's going to receive more light per square meter. And it works out to be a tie. And you can think of it as, of course, it works out to be a tie because both of them catch all of the sunlight. There's no way that sunlight gets from the star to the rest of anywhere without first hitting the sphere. So unless we're splitting hairs with reflected light or changes in the brightness of the sun, just keeping it simple, they both catch all of the star's light. So they're going to catch the same amount. So it is a tie. If one of them had twice the radius, it would have 4 times the surface area, which means it's going to have 1/4 the brightness to get the same amount of sunlight caught. So if you are twice as far away from a star, it appears 1/4 as bright. Right. Different super engineering project. Still have a star. And someone makes a perfectly transparent glass cube. Or box near the star. So the light is going to come in on this far right surface, and it can spread out and go out through multiple of them. So this is not going to block any light at all. So in total, think about the surface of the sphere, how it comes in, how it comes out. Are you going to get more light entering or exiting? And the walls are not reflective. They're the clearest thing that could be.
So it's a transparent sphere or a cube?
It's a cube
Oh,
or a box of some kind because, oh, I did write sphere. It doesn't matter. Either way. Cube, box, sphere, it's a shape. And most people are voting for a tie. And this time it is indeed a tie. So any line that you draw from the star enters once, exits once. So however much comes in, comes out. Another way of thinking of it is it's perfectly clear, so the light's not stopping there. Whatever passes in needs to pass out. So in both of these cases, it is a tie. So really not looking at sunlight as anything other than something to get our thinking started. So light actually is traveling outwards from the star. Electric fields, for now, we're not going to think of them as physically moving, but just pointing. So you're going to have electric field lines which point outwards. But same idea. And we can look at where these electric field lines go, or just follow our way along the paths. So I'm going to introduce a new concept, and that is electric flux. So flux gets this cool symbol. And if it's flux in an electric field, it gets a little e. And we are going to define it as the amount of electric field passing through a surface. So in a simple case, if we have just some imaginary sheet and an electric field. Some of this electric field may go around the sheet, but some of it actually does pass through it. So if it was oriented so the electric field lines went straight on past it, like that, no electric field lines would pass through it. Nothing would be caught. You can think of it as aligning a solar panel to catch sunlight. If you hold it up so it casts almost no shadow, you get it as skinny as possible, the light's not going to hit your solar panel. You get the most light hitting the solar panel if that angle you have is the same as the angle of the electric field. So what is normal? So the electric field is normal to the surface. So how much electric field is caught is mathematically just like how much light would hit the solar panel. It's proportional to the strength of the electric field, or carrying this analogy forward, how bright is the light? It's proportional to the area, and it's also proportional to the cosine of the angle between them. Stronger electric field, more passes through, bigger area, more is caught, more passes through, and the optimal alignment makes a lot pass through. So the cosine of the angle between them. This can be re-expressed as the perpendicular component of the electric field times the area, or the electric field times the perpendicular component of the area vector. Or we can just take a dot product. Where there's all just different mathematical ways of saying the same thing. Good on this concept of flux. What sort of things do we put into fields to measure flux? So you would probably just measure the electric field directly and integrate over it to get to flux. So just probably just measure the electric field itself would likely be easier. Are there devices that are just good for measuring flux? Ichiosis injunction.
I was just wondering if like the solar panel had an analog to something you'd actually put in it.
So changes in flux actually end up being much easier to measure than just flux on its own. So you can measure electric fields directly. That's something that can be done. You could measure changes in flux. Actually would probably be easier than just measuring the flux directly on its own. But looking to changes in flux and what they do is a topic for much later in this semester. Cool. It's possible that the electric field is not uniform, or sheet, which is collecting electric flux, is not flat. It could be curved or have an angle in it. It's a made up thing. It does not need to be a made up simple thing. So in that case, our flux would just be the sum over the little segments, or if things were changing continuously, flux, the integral of all the little segments. So you can just imagine taking a wavy sheet where the electric field is stronger in some parts than the other parts, and just breaking it up into little bits. And figuring out the flux through each bit and adding it up for the total flux. Or you could make your little bits infinitesimal in size, and then we're just integrating over the entire surface. So there are two kinds of surfaces that will be important to us. Surfaces like the ones we've already drawn, which have a boundary around their outside. There's some perimeter there, an edge, and ones that aren't like that and just enclose a volume, a bubble. So something like a sphere or a cube. So if we've got this uniform electric field, what should the flux to the cube be? So some passes into it and some passes out of it. But there's a convention for closed surfaces that things that pass out count as positive, things that flow in count as negative. So this cube with electric field flowing through it ends up working exactly like the perfectly transparent box with sunlight passing through it. Those electric field lines, they all enter, they all exit. So if we're talking specifically about closed surfaces, so instead of something like a flag or a solar panel, something like a bubble or a box, something that completely wraps up a volume. We indicate that the surface is closed by putting a little circle in the middle of our integral sign. So the total amount of electric field that passes out of a closed surface is just the integral of the electric field passing out of each little bit of surface. This really isn't adding much. It just gives us the sign convention of plus is out. So let's do more than just have a definition of what flux is. Let's do something with it. If every line that enters also leaves, the flux will be 0. And going back to the nature of electric fields and electric field lines, those electric field lines they start at positive charges end at negative charges. But they don't start and end in empty space. So the electric flux needs to be 0. If there's no charge inside of the box. Because whatever field line goes in will also go out if there's no charge in there.
So then how is there a flux for like a sheet? Because that doesn't enclose any volume.
Yeah, so this rule is for things that do enclose a volume.
Okay.
So there's no in and out of a sheet. There's just, up and down or left and right. So this is for closed. This is for enclosed volumes. It doesn't work for just a sheet. I guess it's a fair point because a sheet doesn't enclose any charge, but it's for surfaces that are closed. And if we have actual charge that is enclosed, let's go for our simplest possible case. A point charge smack dab in the middle of the sphere. So the electric field on the surface of the sphere, not that hard to figure out. KQ over R squared. And it's going to be outwards, or 1 over 4 pi epsilon naught. Q over R squared. So our flux will be our electric field times our area times the cosine of the angle between them. We don't do this particularly fancy because the electric field is in strength at all points along the sphere by symmetry. They're all equally far away. So you don't need to really fall to ugly math. For our cosine of theta, the electric field goes out, normal to the surface also goes out, so that just becomes 1. So the total flux out is just the electric field times the area. And you know the area of a sphere, surface area? It is 4 pi r squared. So then our flux is the charge over epsilon naught. So I showed this for a sphere of any volume, but if we, instead of using a sphere, I'm sorry, a sphere of any, well, radius, volume, doesn't matter. Use this ugly lumpy blob. If instead of having electric field, we had sunlight, both the red lumpy blob and the black sphere would catch as much sunlight. They'd both catch all of it. If we made a small one, that would also catch all of it. And electric fields follow the same 1 over r squared rule as sunlight does. So that would also catch the same amount of flux. So if it works for a point charge in this middle of a perfect sphere, it's also going to work for a weird lumpy blob. And this is Gauss's law. So the only part that matters for the total amount of electric field leaving a closed bubble is how much charge is inside the bubble. And this is, I think it's profound and powerful. So in the beginning, you might have been wondering, why would you use epsilon naught? Where's this 4 pi coming from? That's just a less efficient way of using our units. When you get to Gauss's law, it comes out cleaner. And that 4 pi you can get from surface area of a sphere in order to cancel all out. So
And what is our epsilon naught in this case?
epsilon naught, so it is something that we've been using before, where k is equal to 8.99 times 10 to the minus 9. Newton meter squared, Coulomb squared. So it is the permittivity of free space.
Professor, is it -9 or +9 for K?
Oops. That little dash should not be there. You're correct. Sorry.
It's okay.
It's the permittivity of free space. It's how well electric fields can, spread out from something. So this is true in nice, pretty symmetric cases, and it's true in ugly, hideous geometries. It's much more useful in nice, pretty symmetric cases because for our sphere, we can just tell that the electric field is going to be the same on any point in the sphere. So if we know the flux and we know the surface area, we can figure out the electric field. So you could do the same things for other nice, pretty symmetric geometries. The law still holds for complicated ones. It's just not practical to use. Right. Any other big idea questions on this one? This one I think is confusing and it might take some sink in time. All right, let's try working with it a little bit. So there's a box and it has 10 to the 11th electrons and 9 times 10 to the 10th protons. So what is the net electric flux out of the box? See if you can work it out. So figuring out the electric field at every point on the box would be not possible because we don't know where the electrons and the protons are. So I don't know a way of doing this without Gauss's law. But Gauss's law makes it quite manageable. So our electric flux, which is the integral over our surface, the electric field, divided with our surface area element, equal to so the net charge in the box is what we would get from 10 to the 10th electrons. Because 9 times 10 to the 10th protons cancel out 9 times 10 to the 10th of the electrons, and we're left with 1 times 10 to the 10th electrons of uncanceled negative charge. So it is the net charge in the box that determines the flux. And we can divide by epsilon naught. And I got a numerical value of 181. And for the units, well, we've got a coulomb up here, which is going to cancel one of those. This newtons is on the bottom of a bottom, which makes it back to the top again. We have Newton per Coulomb meters squared, which does work out. So flux would need to have the units of field, which can be measured in newtons per coulomb, times area, which can be measured in meters squared. Shouldn't the 10 to the 10th be 10 to the 11th? No. So the reason I use 10 to the 10th instead of 10 to the 11th is that 10 to the 11th. Oh, wait. Yeah, it should be negative, though. Because our charge is negative. So our flux out will be negative because things are flowing into the box. Our charge in the box
Professor,
yes.
wouldn't it be better to say that it's just the fundamental charge that's negative because that's just the number of electrons that we have in the box?
It's negative that much times the fundamental charge.
Okay, all right, just moving it around, got it.
Yeah. So yeah, we have negative 10 times 10 to the 10th fundamental charges in the box, or 10 times 10 to the 10th uncanceled electrons. So our net charge is minus 10 to the 10th fundamental charge. So it is what is uncanceled that matters. So if you had a box like this, with one proton and one electron, your net flux out of the box would be 0. You'd have some electric field going like this. So there'd be a bunch of electric field lines that did leave the box, but they all come back in. Yeah, it's the difference between the electrons and the protons. So if you have an electric field line, a path along the electric field that exits and enters, you count that as positive when it exits, negative when it comes back in, and you end up with no contribution. So this positive and negative charge, which are not right next to each other, still don't contribute to the flux out of the box, the net flux out of the box. So there's a cube, and there's some really weird electric flux going on through the faces of this cube. So some of them have 0. But there is some average electric field passing through the faces. It's not uniform on the face, but on the whole, at the top, the electric field is going upwards. On the bottom, the electric field is going upwards, but weaker. So what is the electric flux through the right face? See if you can work it out. So if you want to teamwork it, try rooms 1 or 2. There it is. So this is mathematically not that hard, but conceptually, maybe. So the big idea is we know the total flux out from the box. That is what Gauss's law gives us. So integral of the electric field over the area dot dA. The amount of charge enclosed by the box divided by epsilon naught, but the box is empty, so that is 0. So we can just add up the flux from all of the faces to get the total flux. So and we need to be very careful on what direction these are counting. So for the top one, plus is up. For the bottom one, plus is down. And for the right one, I hate, plus is right. So we don't know what the electric field is at all points through the top, but we do know the average is 5 newtons per coulomb upwards. So our average electric field will give us the flux out through it. And that is going to give us 5 newtons per coulomb times 4 meters squared, 20 Newton coulomb meter squared. From the bottom, it is negative because the electric field is going up. Oh, I didn't say one way or the other ways. Oh yeah, upwards. So it's flowing into the bottom, so that's going to count as negative because plus is down.
Shouldn't we say minus flux to the right because we know that it's going to be flowing into the box?
So I'm sticking with the plus out sign convention. So I'm going to get a negative number.
Okay.
So it is flowing into the box there. So there's a total of 12 Newton meters squared per Coulomb to the left, not the left. So this is just Gauss's law when there is no net charge. It needs to add up to 0. All right, these are true things. Gauss's law is upheld here, but we can use it much more effectively. So last week, there were a series of mathematically intricate to the point of unpleasant problems. We're trying to find the electric field at a specific point. So Gauss's law is good for those problems if everything is very, very symmetric. So for a good example, if you have a sphere with positive charge distributed over the surface, and it's a conducting sphere, and you want to know what the electric field is some distance away from it, that could be a problem because you get an electric field component from everything on the surface of the sphere. So if you wanted to use Coulomb's law very, very carefully, you could take into account this closer bit of charge, and you wouldn't use the average distance, you'd use how far you are to that bit of charge. And you need to take into account that this charge is a little extra far away, and that this charge isn't going to push directly to the right because it's below the middle line. So you could integrate over all of that charge, and it would be rough. Instead of doing that, you could use Gauss's law. So if we want to know the electric field here, we can make an imaginary surface or a Gaussian surface that encases all of the charge. If we made this a perfect sphere, then you know that the electric field magnitude here is going to be the same as the electric field magnitude here, which is the same as the electric field magnitude there. Everything in all directions is the same. Everything is spherically symmetric. So if we find the total electric flux, we can find the electric field at any point on the surface because it needs to be the same by symmetry. So Gauss's law. However, this integral is just going to turn into electric field times area because it's not in varying strength. That cosine factor is 1 everywhere. So it's just electric field times area in this nice, simple example. Solving for E. It's just what you'd get for Coulomb's law if all the charge was in the center. So the fact that it's spread out doesn't end up changing anything. What if instead of wanting to know the electric field outside, you wanted to know the electric field halfway between the middle of this metal sphere and the edge? So if these are concentric spheres drawn by a better artist than me, what will our electric flux through this new dotted line be? Well, no charge is enclosed here. And the electric field needs to be the same at all points just by symmetry, or the same magnitude at all points. So it needs to be radial by symmetry, and there's no way that we can get anything but 0. So inside of this, our field needs to be 0. We can also use it for geometries that are not spherical. So at the end of last week, there was the problem of the very, very, very long line of charge. So if we have this long line of charge, putting it into a sphere is problematic. This is not a spherically symmetric case. But if we let it be long enough that we can just assume it's infinitely long, and we wanted to know the electric field at this point, instead of making a spherical Gaussian surface, we could make a cylindrical one. Where the very long line of charge passes up through the middle of the base and up through the middle of the top, along the symmetry axis of our Gaussian cylinder. So this is a closed surface. There's an inside and an outside to a cylinder. There is charge inside. So Gauss's law can be used here. By symmetry, there shouldn't be any electric field passing through the top or the bottom, because only up and down electric fields would matter there. And there's as much above as there is below, so there shouldn't be any electric field there. So the only electric field that we need to worry about is what's going radially outwards. Okay, Gauss's law. Because the electric field should be the same at all points on the sidewall of the cylinder, we can just turn that into electric field times the area of the sidewall. So our electric field is again Q enclosed over epsilon naught times the area. Our charge enclosed is going to be the height times how many coulombs per meter we have. Our area is the height times the perimeter of the circle. So we get lambda over 2 pi epsilon naught r, which is way, way easier than the method of last week. So this does have some downsides. We needed to assume that the length was infinite or near infinite in order to have enough symmetry for this to be practical. But if you have one of those nice cases where there's enough symmetry to use Gauss's law, it makes things much, much easier. Good on this. The big ideas are not easy, but I think they're neat.
Didn't we kind of
Sounds
choose
pretty
that
cool.
radius like at random?
Absolutely.
So then like, how can we, like, couldn't that radius really be anything?
Absolutely.
Make it 1. Easy as.
Make it 1 meter. And that will give you what the electric field is 1 meter away from our positively charged wire.
Fascinating.
Okay.
So if you look at the electric field 2 meters away, you get a different result, which makes sense. You're farther away, it's weaker. But another thing that's cool is it doesn't have the 1 over r squared law anymore. If you're getting away from a very long wire, it actually follows the 1 over r law. We also chose the height arbitrarily, but it ended up canceling out and not mattering at all because it's a made up height. One other important geometry is the sheet or pillbox. So if there is a infinite sheet of charge, a useful shape for a Gaussian surface is going to be a box or a cylinder, but this time half on one side of the sheet and half on the other side of the sheet. So the sheet is cutting our pillbox in half. So this time the electric field is all going to be going out of the top and bottom I'm sorry, of the right and left part of our box, not the walls connecting them. So our first bit is entirely the same. For our charge enclosed, that's going to be equal to the area of that circle will just be A. So it's going to be the charge density times the area. And we're dividing by the area that the electric field can come out through. So it can go out to the left and it can go out to the right. So for the flat geometry, we get our charge density divided by 2 epsilon naught. And as you get farther away, the electric field actually does not change. That will be it for today. Reminders, quiz on Coulomb's law on Wednesday. Homework, new homework is coming. Homework solutions are coming. And yeah, when we next meet, we will continue working with Gauss's law. It takes some work to get comfortable with it, and we're not done with it. Any questions before we end for the day?
Tomorrow's lab, just confirming, is just part B, right?
Yes. So for people in my lab sections, it's only going to be group B showing up, and it's going to be pretty quick. Just a overview of the semester, how lab reports are going to work.
Thank you.
Thank you, Professor.
Recordings posted. I have a link to it on Canvas, but I can also share it in the chat.
Excuse me, Professor, lab is tomorrow or Thursday?
Some people have it tomorrow. Some people have it on Thursday. Some people have it Tuesday of last week or Thursday of last week. So I have multiple lab sections, and some people don't even have me for lab.
Oh, I have your lab. Do you have lab on Thursday at 6 o'clock in the evening?
I do. That's one of mine. Yes.
Okay. Okay. Thank you so much.
You're welcome.
Thanks, Professor. Have a good rest of your day.
You too.
Thank you, Professor. Bye.
Bye.
Quick question.
Yes.
Are we doing chapter 22 next lecture, or are we already in chapter 22?
Next lecture, we will be doing more work in chapter 22.
Okay.
I'm not sure if it's going to be entirely chapter 22, but that's going to be the focus. We have more work with Gauss's law in chapter 22.
Okay, just checking. Thank you.
Sure.